Chapter 10.3 is on polar coordinates. Now, polar coordinates is something you already learned in pre-calculus, but let's review. When we have this grid right here, this is what we call the Cartesian plane, right? Where we have an x and a y and all my grids run parallel and perpendicular. Now, when I move over a distance to, for example, the point 1, 1 on the Cartesian plane, I move from here. This x value is the distance from the y-axis out to my 1, my x equals 1. And then my y value of 1 is going to be visible here. So the point of reference, the real distance that these two numbers show is to the axes, right? Because this is a y of 1, and this is an x of 1. Right, an x distance of 1. Now, in the polar coordinate plane, I don't really care about what the distance to these axes are. What I really care about is the distance to the center here, right? So that happens, so when do you see polar coordinates? Polar coordinates you see, for example, when you're looking at a submarine and there's a cursor that spins around. What you really care about when you're in a submarine is if this is you really only care about how close certain objects are from you. Okay? So the way that works is at a certain angle. So this is you. This is the point of reference here now. So what we do is we overlay a bunch of circles and make the center that origin right there. Okay? So you have a distance from the center, for example, which no longer relies on this x-axis and this y-axis, but it relies on this point of origin, the center of the circle. Now, how do we determine the distance? Well, that's just by the radius, right? So this would be a radius of 1. Over here would be a radius of 2, right? Radius of 3, this way, okay? And then, of course, you need to know an angle. You need to know some sort of an angle. What's the spin? So like I said, in a submarine, you usually have this thing spinning, and it's beeping, and it's identifying objects that are close to you, right? So if you see an object way out here, it's not that far, and then of course, as it goes around, as time goes around, it gets closer and closer. That could be danger. In movies, it's like missiles or torpedoes or whatnot. So let's take a look at this Cartesian coordinate 1, 1. That's right here, right? So this exact same point, I can actually change it into polar, right? And all it is I'm indicating an r and a theta. Some sort of radius, which looks like it's bigger than 1, further than 1 from the origin, right, but less than 2. So around 1.4-ish, maybe 1.5. And then the theta here, this being our reference point from this 0 degrees, is going to be exactly 45 degrees. And that we know because it's an isosceles triangle, 1, 1, right? So in radians, 45 degrees would be pi over 4, right? Let's take a look at another example. Let's say we have polar coordinate. We're given the polar coordinate of 2 and pi over 3. So now again, in polar coordinate form, this is r and this is my theta. So the radius is going to be, here's 1, here's 2, and again, the importance is not the distance to the axes, but to this origin right here. So it's going to be on this ring right here, where r is equal to 2, on this ring. And then my degree is going to be pi over 6. So that's going to be about 60 degrees. So I'm going to take this and I'm going to move this to around 60 degrees. Actually, I have a protractor right around here. It looks like it's going to be 60 right there. Okay. So 2 pi over 3 is going to be this point here. What if I wanted to change it to Cartesian coordinates? Now again, it's the exact same location on the map, except this time I'm drawing these x and y axes. And it looks like it's going to be approximately 1 and 1.8, 1 and 1.8-ish. So this is approximately. Okay. How can we tell for sure? Well, I know this here is pi over 3, right? So let's draw my right triangle. And I know this hypotenuse here is a distance of 2. I am looking for this x and this y. And of course, we can use our SOHCAHTOA, our trig. So adjacent to solve, we want to use the adjacent and the hypotenuse. So that would be cosine. Adjacent over cosine of pi over 3 is equal to the adjacent over the hypotenuse. Cosine of pi over 3 is 1/2 is equal to x over 2. So x is equal to 1. Yay! Now the y value is going to be sine of pi over 3 is equal to opposite over hypotenuse. So sine of pi over 3 is going to be square root of 3 over 2 is equal to y over 2. So then y is going to equal to the square root of 3, which is approximately 1.7071. Okay, so 1.8 was pretty good. Looks like it was closer to 1.7. Okay. Now what if we generalize that? Instead of doing very specific ones, what if we generalized it to any r and any theta? Okay, any r and any theta. So we'll just generalize everything. This is my theta and this is my r. We're solving for x and we're solving for y. We know that cosine of theta is equal to adjacent over the hypotenuse. And we know that the sine of theta is equal to the opposite over hypotenuse. When I solve for x, x is going to equal to r cosine theta, and y is going to equal to r sine of theta. Okay, and this will always be the case. Therefore, we have two very general formulas for this. Okay. What other formulas do we know in polar coordinates? We also know that each of these rings, we know the connection between, if each of these are circles with a center at the origin, we also know the equation of all of these circles. Okay, it's going to be x squared plus y squared equals r squared. And those are basically the only three formulas you really need to know for polar to transfer between polar to Cartesian and from Cartesian back to polar. Okay, these are the only ones you're going to do. If you want to get rid of both all you want to do is get rid of both the r and the theta in order to change to Cartesian, and get rid of the x and the y in order to change to polar. So now let's take a look at some polar functions. Now here an equation is written in polar form. There's still the Cartesian grid is still here, it's invisible, but we still have our x-axis here and our y-axis here. And here x is 1, x is 2, y is 1, y is 2, and so forth. Now, but this one, we have a radius that varies with whichever input, the degree input that I put in. So for example, when theta is 0 degrees, which is where my green cursor is right now, I have cosine of 0, which is going to be 1. So that means when it's 0 degrees, my output, my radius, is going to be 1. Now what happens if I move this to, for example, pi over 6? So r of pi over 6 will be cosine of pi over 3, which will give me 1/2. That means when theta is pi over 6 right here, I'm going to get a point of 1/2. Now I can keep going, and then, which I've already created a table for us right here. So take a look at 0, I have a radius of 1. At pi over 6, which is the same thing as 2 pi over 12, I have 0.5. Now in this case, I've done it by every pi over 12 because each of these are 1/12 of pi right now. So at pi over 12, it looks like it should be my radius, the distance from the center, from the origin, is 0.866, somewhere around here maybe. And then at pi over 4, which is these red lines here, my distance should be 0. Now remember what I had said, in polar and in parametric, you not only have kind of the pathway, but you also have a direction. So this graph went from 0 here to this one, to this point, to this point. Right? So it's going in this direction. Let's take a look at the next one. The next one is, what's the next one? 4 pi over 12. It looks like I'm here at negative 0.5. Now what does it mean to have a negative radius? A radius of negative 0.5. Well, you see this line right here? This is my 4 pi over 12 line, or my pi over 3 line. In this case, a negative radius, this is in the positive direction, wherever my spinner is, but then instead I'm going to follow it in the opposite direction and go negative. So that will be negative 0.5. I'm going to move it to the next one, which is going to be right here. So at 5 pi over 12, I should be at negative 0.866. So that means I'm going to follow that to the negative side and go to 0.866. And then I'm going to go to pi over 2. This is positive pi over 2 because I moved in the positive direction, except at positive pi over 2 I need to go to a radius of negative 1, which again, this would be positive 1, but I'm going to go backwards here to a radius of negative 1. So now it looks like the direction in which my object is moving is along this way. So I'm going to continue this. The next one here, it looks like it's going to be negative 0.866, right? The next one here is going to be negative 0.5. The next one at 3 pi over 4 is going to be back to 0. So now I have this little, what we call a petal, and it should be smooth, right? So let's say I keep going. I keep going and I go basically to the next one after 3 pi over 4. So it's positive. It's now back in positive 0.866. No, wait. It's back at 0, so now it's back at 0.5. Sorry about that. It's 0.5. The next line over, 0.866, 1, 0.866, 0.5, and 0. So now it's going this way. Right? So we have gotten currently up to, follow it along up to this point, right? So after that, if I keep following along, it's going to get me up until, so I'm going to go until 5 pi over 4, which is 0. So from here, I got to go negative 0.5, it looks like. From here, negative 0.5, which is going to be here, and then negative, when this green cursor goes here, it's negative 0.866, then negative 1, negative 0.866, negative 5, and then back to 0 at pi, at 3 pi over 2. And then the next part will give me all the way up until, as I finish the curve, up until 2 pi. and it's going to look something like this. And that is only, again, I can keep going beyond my 2 pi